Okay, so I'll talk about the CountEverything, a project that we have been working in the last 12 months. So a little bit of the background. Biomedical data and healthcare data are often distributed in secure computing enclaves across many organizations. However, interface that allows the user to operate on these data in a secure and privacy-preserving manner. So this particular project is a collaboration between BioCaddy, IDASH stands for Integrating Data for Analysis, Anonymization, and Sharing, one of the CPC Center, together with three BD2K Center of Excellence. The goal here is to build interoperability between the APIs. So we want to present integrated interface to user so they can give a query touching all the data sources from these three centers, and then each query gets decomposed into subset and final answer being integrated using the secure service provided by the BioCaddy UCSD API. So during the last 12 months, the different centers have been developing different APIs. From the Center of Big Data for Translational Genomics at UCSD, they developed the J4J, which stands for Global Alliance for Genomics and Health API to cover a variety of genomic data types. And they also deposit 1,000 genome data in their demonstration service. And MD2K, which is the Mobile Sensor Data to Knowledge Center, implemented Open mHealth API and schemas to cover the core mHealth data type, and they also developed API and a demonstration server. Similarly, Picture from Harvard, which stands for Patient-Centered Information Commons, they also developed API to cover a variety of clinical and environmental data types, and they utilized public data in their demonstration service. We, BioCaddy, developed the integrated count query across all these three APIs, and we implemented layered anonymization protecting schemes. So I will focus on the experiment in this talk. We mainly invested our effort in the following four aspects. So first, we developed integrated schema and set a set of 2,504 global IDs across all centers so that they can query and get some results back. We try to implement it seamlessly integrated with our JavaScript-based user interface. From Picture, we utilized a number of data attributes, including like systolic and diastolic blood pressure, gender, age, race, body weight, height, BMI, etc. And similarly, we utilized systolic and diastolic blood pressure, sleeping duration, body height, body weight, body temperature, body fat percentage, blood glucose level, and at the Center of Big Data in Translational Genomics, we used their API to call these four different attributes, including reference name, start position, alternate base, and assembly ID. All these APIs supports RESTful APIs, and we first developed a protocol based on the GMW, which is a zero-knowledge protocol, ensuring no information leakage in a completely decentralized environment. So the basic ID and only returned result, which is the count of patients satisfying the query terms to the user. The protocol is essentially calculating the intersection in this Venn diagram. For example, if I want to query the number of patients who has glucose over 1, there are patient IDs who match the query condition, and use the GMW to calculate the intersection showed in this Venn diagram using GMW. A total of 8 million calculations to be done on this protocol, which makes the model doesn't scale very much. So we tried a second protocol, which is based on homomorphic encryption. In this mechanism, we actually introduced a different structure. Instead of using the peer-to-peer communication, we utilized the hub and spoke architecture, In this scenario, we used BioCaddy to serve as the crypto service provider to generate public and private keys, using the iDash server to serve as the CountEverything processor. So individual centers encrypt their data, sent to the CountEverything processor, which get calculated, and finally combined results get decrypted using the CSP. So there are three roles as just mentioned: the data owner who provides data for counting, and they also encrypt the data and send to the processor. Note that the processor and the data owner share the same public key, so the processor can combine the results using the homomorphic additive operation, and then final results get deciphered at the CSP. So in a nutshell, this is an illustration of how this mechanism works. The CSP generates both public and private key, and the public key sends to the data owner and HME processor, and the encrypted results get combined at HME processor. So this table shows how this is actually calculated in our mechanism, which is using a Palea schema. So the idea is if center A has patient satisfying the query, the partial query, then we can annotate it with a 0. Otherwise, it's a random. But after homomorphic encryption, there's no way to tell 0 and random. But homomorphic encryption supports additive operation. So we sum up all the corresponding rows and get a number. So 0 corresponding to a patient who has met all the subqueries. And then we finally shuffle this the encrypted code and then send to the CSP to get deciphered. In final step, we only need to count the number of zeros to obtain the result. So the system architecture looks like this. So we start with a query from the user, which gets decomposed, and our HME service will be called depending on whether the user chooses to use our secure protocol. Because we also implement a non-secure protocol to be compared with our secure protocol to ensure the result is correct. Once the user selects the secure operation, this is a detailed workflow which shows that all the centers send encrypted results through the Apache Tomcat and then passed by our API, and finally the count gets decrypted at the CSP. We also developed a waterfall query models, so user can dynamically interact with this interface by expanding or adding more conditions. And then the two buttons at the bottom of the page. So once you click the green button, the orange button has a biohazard, which means it's a non-secure comparison. It shows how the non-secure procedure was conducted. Otherwise, if they choose the green button, the secure operation only reveals the final count, which is 15 in this case, satisfying all the constraints. So finally, we also benchmark the performance of our model using different size of the data. So the first column in the table shows the size of the patient at different centers from 100 to 10K. And it shows on the right of the figure that these calculations are mainly dominated by the cost of encryption and decryption. And the actual computation on the ciphertext is marginal. We also benchmark the memory cost of 2,500 records using our HME protocol. As you can see, like counting all the memory costs from the 3-center HME processor and the CSP, the total memory cost is about 125 megabytes. So I want to thank all the teammates at UCSD and the participating centers, as well as the NIH grants to support this research. So thanks for listening. I'm ready for some questions.